Hey everyone, welcome to the Kubernetes full course, complete hands-on. In this course, I'll be teaching you the most important and essential Kubernetes concepts. Many people believe Kubernetes is difficult to learn, but my goal is to make these concepts simple, clear, and easy to practice. Let's begin this course by comparing Docker and Kubernetes. Docker is a platform that allows us to package applications into containers and run consistently across multiple environments. In production environments, we need to run many containers. Docker is not capable of managing tens, hundreds of containers in production environment. That's the reason we want Kubernetes in picture. Kubernetes is open source platform for container orchestration. Why we should use Kubernetes? Number one, it can efficiently schedule containers onto the nodes. For example, in production, we have 10 nodes and I'm giving an application to this cluster and saying deploy this application with 3 copies. Out of 10 nodes, Kubernetes should figure out which nodes are the right nodes to schedule these 3 pods or containers. We'll see more about that in the course. Secondly, it can automate the deployments, which is very important in production environments. Auto healing. For example, I gave application 1 to Kubernetes saying deploy 3 copies of this. For any reasons out of 3, let's say 1 copy went off. Now Kubernetes can automatically bring a fresh copy to meet the desired capacity 3. Automatic scaling. We can automatically adjust number of replicas based on the traffic. If traffic is increasing, we can increase number of copies. If traffic is decreasing, we can reduce number of copies. Likewise, there are many features implemented inside Kubernetes open source platform. Let's see the tools required for this course. Number one, Docker Desktop. We must install this on our local machines. Go to internet and search for Docker Desktop. Choose the right option for your operating system and install it. The next tool is Minikube. Minikube is used to set up local Kubernetes cluster. I don't want to set up a real world Kubernetes cluster in the beginning. Anyways, I will use Elastic Kubernetes cluster in the end where I show complete CI/CD using EKS and Argo CD. But most of the concepts we can practice within our local environment using Minikube. Let's see how to install Minikube. I'm saying Minikube install MacBook. Open the first link. This is the official page for Minikube. Use this page for installing Minikube on your local machine. And if you see container or virtual machine manager, these are the supported containers or virtual machine managers for Minikube. We should install Docker Desktop that is used by Minikube for creating local Kubernetes cluster. After Minikube, the last one is kubectl. Kubectl is command line utility which is used for communicating with Kubernetes cluster. Let's see the document for installing kubectl command line utility. We have multiple options for installing on Mac. One is using curl. The second one is using Mac OS Package Manager. This is the easiest way of installing kubectl on MacBook. Let's start Kubernetes local cluster using Minikube. Make sure your Docker desktop is up and running. Run minikube start command. This takes few seconds to set up the cluster. Minikube is successfully started, and see this information, it automatically selected the Docker driver. Let's use kubectl command to get nodes. There is one node which is set up by minikube. Let's say we want to mimic a real world production cluster. We want to have multiple nodes. That is also possible. Let's use minikube node add. This is adding the second node to the cluster. Likewise, even when you start a minikube cluster, you can mention number of nodes you want to create. Let's use kubectl get nodes. Yeah, there are two nodes running in local. It's time to deploy our first application on Kubernetes. To do this, we need to understand the basic building block, that is the pod. A pod is a smallest unit of deployment. A pod can contain one or more containers. Mostly, we see applications deployed on pod with a single container. Pod shares network space and storage space. That is, containers inside same pod can communicate with each other using localhost because they are sharing the network space. Pod gets an private IP. This IP is reachable within cluster from any node. We can deploy applications using imperative approach or declarative approach. In declarative approach, we put all the details in YAML document. We pass it on to Kubernetes cluster. Cluster takes care of creating the resources accordingly. In imperative approach, we put everything in the command itself. Let's see both the approaches. First, let's go with imperative approach. kubectl run, specify name of the pod. I want to create nginx pod. Provide image. I am taking nginx latest image. We also should specify the port on which nginx listens. By default, it is 80. It created a pod successfully. Let's check its status. Use kubectl get pods command. Name of the pod, status is running, age is 11 seconds. There is one container inside the pod that is up and running. That's the reason it is saying 1/1. Let's say we gave two images, it creates two containers. If both containers are up and running, it should show 2/2. If you want to see more details about this pod, use kubectl get pods -o wide. This provides on which node it is running, the IP address of the pod as well. This IP address is private within Kubernetes cluster. It is reachable from cluster, inside the cluster, from any node or any pod. But we can't access this IP from the outside world. Here is a representation of the pod. If I want to access this pod from my local laptop, which is not inside Kubernetes cluster, it is not possible. But how do we expose applications to the outside world? We use either service or Ingress controllers, which we will discuss later in this course. But I want to test this application. There is one command which exposes this application to us via a port mapping. kubectl port forward. I want to port forward the pod. Its name is Nginx. I want my localhost port 8080, and of course Nginx is listening on 80. After running this command, I can open my browser, put localhost 8080. The traffic is routed to Nginx, which is running inside Kubernetes cluster. This is only for the testing purpose, and this is not the way we expose applications to the outside world in real world situations. Enter. In the browser, put localhost 8080. The request is coming from Nginx, which is running inside Kubernetes cluster. Now let's see how to deploy a pod using declarative approach. Let me go onto my desktop. I created a folder K8s full course. Go inside that. As of now, it is empty. I want to use Visual Studio Code for creating this YAML document. Open Visual Studio Code. So here, create a new file. I am naming this nginx.yml. I can use GitHub Copilot for generating this file, but let's use Kubernetes documentation to get YAML document for Kubernetes pod specification. Go to pods. Yeah, you'll find a sample example for the pod. Copy this, paste it here. Please ignore this warning, but let's focus on this YAML document. It has API version, the kind of resource, that is pod. To specify name of the pod, we put name under metadata. So giving Nginx as a name, and the specification for creating this pod. I said pod can have multiple containers. Even in this example, we are using single container because this is representing one container information. This is name of the container, image to create the container, the port on which it listens. I want to delete the previous one, which was created using imperative approach, and create a fresh one using declarative approach. kubectl delete pod name of the pod. I want to use kubectl create -f provide YAML file reference. See, in the command itself, I am not giving all the details. I am not telling which image to use, on which port number it's going to listen. No, I'm simply saying create a resource and read everything from YAML document. Enter. Exactly, it created a pod. Let's check the status of the pod. Name is same, running state, there is one container inside it, and that one container is up and running. If you want to test this one, use same command kubectl port forward. We are forwarding the pod slash name of the pod. It must be Nginx, and 8080 is my local host port number. This 8080 can be any available port, But the right hand side 80, that must be 80 because Nginx is listening on 80. If Nginx is listening on some other port, then we need to specify that exact port here. Enter. Open a new tab. Perfect. The application is up and running. Let's go through few important Kubernetes pod commands. For example, something is going wrong inside the pod, application is not coming up. I want to check logs. Use kubectl logs command. This is the log coming from Nginx pod. If you want to get logs from previously crashed pod, not the current one, then put ---- previous. In our case, there is no previous terminated Nginx pod, it will not work. Sometimes we will have a situation where we should go inside the pod and check for specific files for troubleshooting purpose. For that, use kubectl -it. It should be exec -it, name of the pod, after that ---- space bash. This command takes us inside the pod. If you list out files, we are listing out files and folders inside the pod. To come outside of this pod, use exit. We are again back to our actual terminal. While checking logs, we did kubectl logs command. Correct? Let's say inside this pod we have multiple containers. I want to check logs of a specific container, then use -c container name. Because there is only one container, its name is Nginx, and we get that log. If you have one more container, if it has a different name, provide its name and get logs specific to that container. Now we understand the concepts of pod, but pod is not resilient. That is, if pod crashes for any reasons or the node on which this pod is running that crashes, this pod is not automatically healed. Kubernetes will not create this pod again for you. This pod is permanently gone. Usually, we do not deploy applications on Kubernetes using pod specification directly. We use deployments. I will cover about deployments after some time, but right now I want to explain ReplicaSet. You can think of ReplicaSet as a wrapper on top of a pod. You can see here, it takes a value replicas. Suppose we are deploying this application in production. I want 10 copies of the same application for high availability and scalability. Use ReplicaSet, provide replicas 10, deploy it, it creates 10 replicas. Not only that, it makes pods resilient. If any of the pod crashes, out of 10, let's say 2 pods crashed for some reasons, ReplicaSet recreates those 2 pods to meet 10 as a desired capacity. Let's go to Kubernetes documentation for ReplicaSet. Go to ReplicaSet and see this YAML document. So this one represents container specification, replicas. You can give your own value for replicas and see the kind ReplicaSet API version. Like I said, every resource in Kubernetes is represented as an API resource, but we don't need to really bother about what exactly it is. That is taken care by Kubernetes internally. But when we use API version, we should make sure we are providing the right version. For pod, we used v1, and for replica set, we are using apps/v1. Get this from documentation and don't worry too much about that. Let's copy this. Let me create new file, nginx-rs, meaning replica set. I want to change this according to our requirement. I don't need labels for replica set. I want nginx as a name of replica set. I'm fine with 3 replicas. Let me change match labels. Containers name nginx. Image, let me copy from nginx.yml, this one. Alright. Replica set creates 3 replicas. How this selector works, it's going to check for pods with this label. And here I said from template onwards, it is pod specification. Pod has a label app nginx. Make sure this label is matching with match labels. Otherwise, it's going to fail. To reiterate, this is name of the replica set. We're saying number of replicas we are interested in. It's going to create 3 replicas using match labels. It's going to match this label against pod labels and accordingly create number of replicas. Let's run kubectl get pods. There's one existing pod which is directly created using pod specification. Let me delete it. The command is kubectl delete pod, name of the pod. So now I want to deploy 3 copies of pod using replica set. kubectl create -f. This is to specify the file. I am not giving nginx.yml that contains just pod specification. I am giving nginx-rs.yml. Let's do kubectl get pods. There should be 3 copies, of course. Let me also do kubectl get replica set. There is 1 replica set. Desired is 3, current is 3, ready is 2. It's bringing 1 more. After this becomes running, ready also becomes 2. Now it created 3 replicas. And be aware, pod names cannot be same, because in the same namespace, at least we'll talk about namespaces later. If I want to create 3 pods with same name nginx, it's not possible. This random value is created by replica set for us to keep names unique. I told you replica set makes pods resilient. Let me go and delete 1 pod and see what happens. kubectl delete pod, name of the pod. Now out of 3 we got only 2, but according to replica set it should find 3, and see what happens here. We see 3 again, and notice the last one, its age is 12 seconds, meaning after I deleted 1 copy, it automatically recreated a fresh copy to meet the desired capacity. Suppose you want to permanently delete all 3 copies, you should not delete pods directly, you must delete the replica set. kubectl delete, instead of replica set we also can use a short name or S. Name of the replica set, it has to delete all the pods as well. It's all gone. A deployment is higher level abstraction that manages replica set and pod. The key features of deployment is rolling updates, meaning let's say we already have an application running with version v1 and it has 10 copies. Now we want to roll out v2. What happens in rolling updates? It not recreate all 10 at once. This causes downtime. Rather, it's going to gradually update all the pods running inside the Kubernetes cluster for this specific deployment. Let's say we want to roll out only 10% of pods at a time. Out of 10, 10% is one pod. Pick that pod, replace with v2. And again, do this for all the pods available in the cluster for this specific deployments. With help of rolling updates, we achieve zero downtime deployments. That feature is part of deployment object. And also easy rollback. If something goes wrong in the deployment, with a simple command, a kubectl rollout undo command, we can easily roll back to its previous stable version. And as usual, we know replica set is therefore to maintain desired number of replicas and pod which runs containers inside it. Let's go ahead and see deployment in action. Let's search for Kubernetes documentation. Copy this YAML document. Let's create a file in Visual Studio Code. Paste it. Let's change this according to our requirement. I want to simply call it Nginx. This is name of the deployment. Labels for the deployment. In this case, labels under deployment is nothing to do with the replica creation and so on. But what is important in match labels? See, replica set going to create 3 replicas by looking for pods with match labels. So app nginx. So this one should match with the labels defined under pod specification. See, we actually do not need pod YAML, replica set YAML. We can delete nginx YAML as well as replica set YAML because we're not going to deploy applications as a pod or replica set directly. We use deployments for deploying applications onto Kubernetes cluster because it comes with a feature called rolling updates and rollback. Let's create deployment using kubectl apply command. The difference between kubectl create and apply is create will newly create the deployment. If I run second time, it is going to fail because a deployment with same name exists. But when it comes to apply, if deployment is not yet created, it creates. If it is already created, it updates. Deployment is created, it internally creates replica set that in turn creates 3 replicas. Let me say kubectl get deployment, it's there. Likewise, kubectl get replica set. We did not create replica set directly. Remember, this is created by deployment. Let's also say kubectl get pods. Of course, yeah, there are 3 pods created. Actually, I want to show how rolling updates and rollback works in deployments. In place of Nginx, let's use Python application. I already have image with 2 versions, that is with tag v1 and v2. So let's delete Nginx deployment. Let's go to VS Code, update it for Python application. So here, pyapp, update it everywhere. Let's make 10 copies. Let's deploy this. Yeah, almost all the copies are in running state. I made one mistake. Container port is 8000. Let me delete and recreate all the ports. To test this, let's do port forward. This time, I want to port forward deployment. Name of the deployment is pyapp. I want 8080 to be my host port and 8000 is the container port. Yeah, we see the response from a Python application running inside Kubernetes cluster. Let's stop port forward. I want to update the version of Python application to v2. Nothing but we want to roll out the next version v2. Go to deployment YAML, change from v1 to v2. So run a kubectl apply. Now what apply command does, the deployment is already there, that is running v1. So it updates that with v2. Let's see kubectl get pods. So now we have total 13 containers, right? Out of that, you see this one. It is rolling out updates on 5 containers while other containers are still running. I mean, other pods are still running to maintain the high availability and zero downtime. Let me do kubectl get pods. Now, almost all the pods are in running state and see the time difference between a few pods. 40 seconds, 49 seconds, 41 seconds, 39 seconds, right? So this indicates it's not recreating all pods at a time. It is doing a rolling update. Let's do the port forward and check the output. Let's do refresh and see that one. We see the next version where v1 the color was green, v2 the color is red. Let's simulate a failure deployment. Something went wrong in the deployment, that is v2 current version. I want to roll back to its previous version. Let's see how to do that. A kubectl rollout. undo, deployment, name of the deployment. We rolled out V2. I want to undo that. Let's see kubectl get pods, and see there it is rolling back to previous stable version. It's again using rolling updates to maintain zero downtime. Let's do port forward. Let's refresh the page. It successfully rolled back to previous stable version, that is PyApp EKS v1. So we should always use deployments for deploying applications. We should not really use directly pods or replica sets. Let's understand why should we use Kubernetes service. In a Kubernetes cluster, let's take two applications. App 1, which wants to connect with App 2. Here, it can use IP address for communication with App 2, but there is a problem. The problem is the IP address of the application 2 can change, because in Kubernetes cluster, pods are ephemeral. They are designed for recreation so often, so IP is going to change. Now application 1 cannot keep track of those changing IPs dynamically. It is very difficult. So when these IPs can change, number one, let's say there is a node which is running this pod. We are taking out that node for a maintenance. What we should do, evict all the pods running on this node, schedule them onto a different node. In that case, IP address will change. The second case, we may have autoscaling in place. So let's say now we have 3 instances of pods. After some time it can become 5. Again, when load decreases it could become 2, 3. After some time the IP addresses can be completely different. That is second reason why IP addresses of a pod can change. Number 3, very common, when we do a new release, right? Let's say currently we are running version 001 for app 2. We prepared release 002. When we roll out this new feature using deployments, let's say, old pods get terminated and replaced with new pods which contains new features. These are the reasons why IP address of a pod can change. So that's the reason app 1 in this case cannot directly talk to app 2 using its IP, which is going to change very often. So that's the reason what Kubernetes has done. It came up with a concept service. So this service here, it is not a resource like a pod. Service will never go down. In the background, service is simply a network rule with a stable IP address. How it works, right? Now app 1 will not directly talk to app 2. Instead, it talks to its service on its IP address or using a service name. Even though the IP address of service can be used, but we can still use name of the service, which can be same and consistent across multiple environments. Now let's see what are the features offered by service. For example, to achieve high availability and scalability, we added more replicas. Those pods has to be load balanced. That can be done by a service. Now let's see what features are offered by service in Kubernetes. Number one, provides stable network endpoint, stable IP address or stable service name using which applications can talk to app 2. Number 2, load balancing set of pods. Because of autoscaling, we want to scale out when load increases, scale down when load decreases. So those pods can be load balanced by service. Number three, service can help us to expose applications to the outside world. These are the main features of service in Kubernetes. Now we understand services. Why should we use them? Let's walk through service types. Parallelly, I will show demonstration of creating services in Kubernetes cluster. There are different service types provided by Kubernetes. First one is cluster IP. When you create a service by choosing type cluster IP, what exactly it means, you can access this service only within the cluster. It gets one private IP and this is accessible only within the cluster, and you cannot access service type cluster IP from the outside world. Let's go and create a service. Let's open Kubernetes documentation for service. I want to take this example service YAML file, copy that. We already have deployment file for Python application. Let me rename this file PyApp deployment. All right, create a file. PyApp service.yml, paste it. I want to change this file according to our requirement. We're going to deploy this deployment which creates 10. Let's change it to 3 replicas. These pods gonna have label app by app. When you deploy a service, here right, we have selector. Under selector, you must provide keys app by app. This one here under selector must match the labels of the pod. Only then service going to load balance all 3 pods we are declaring in this file. In our case, target port is 8000. It must be 8000. And the port on which service itself listens can be anything. I'm keeping it 80. Let's change the name PyApp service. Let's mention type. Type cluster IP. We got 2 files, deployment and service. kubectl apply -f. I want to apply everything in current folder, all the files. I'm using dot. It created deployment as well as service. Let's check kubectl get pods. There are 3 pods. Our expectation is the service we created must load balance these 3 pods. I want to run kubectl describe on the service. Notice endpoints. We got 3 IP addresses of 3 pods. Let's run kubectl get pods -o wide. Notice these IP addresses, right? And they are matching with endpoints. You know how these pods are tied up with this specific service using labels. Under pod specification, we got labels. There is one label app by app. In the service selector, it is looking for pods with labels app by app. This is how service and pods are getting connected. When I send request to service, it's going to load balance 3 pods in our case. I want to show how we can communicate with service. For that, I'm going to deploy one pod, which is a BusyBox pod. I will go on to that pod and send request to service and see if it responds. Let's create new file, busybox.yml. This is a pod for testing service. Let me clear the screen. Let this BusyBox come into running state. It is running. I told you we can access service type cluster IP only inside the cluster. BusyBox is also running inside the cluster. Let me go on to BusyBox. From there, let's send request to service. Let's also get the IP address of service. Yeah, this is our service. IP address of the service. Okay. kubectl exec -it, name of the pod --bash. Okay, let's try sh. Yeah, see, sometimes bash works, other times sh. We are inside the BusyBox. From there, I want to send request to the service. Ping. Or let me send a curl request otherwise. Curl http. This is service IP. It's listening on 80. When we send request to this service, it load balances to the pods running in the background. Okay. Curl command not found. Let's use wget and see the response. We are sending request to the service IP on 80. That is forwarding the traffic to one of the backend pod. So pod is running Python application. You know about that. Instead of IP, let's use service name. I told you we can access service on its IP address or on its name. Name of the service is pyapp-service. Remove IP address, provide the name and see the response. The IP address of the service going to remain same all the time. Okay, when should we use cluster IP? Suppose we are deploying a database inside the cluster. Obviously, this database must be accessible only within the cluster. No one from outside can access database directly. So for this, we want a stable endpoint. So create a service of type cluster IP so that applications running inside the cluster will access this database. No one from outside the cluster can directly access database. Let's move on with next service type, node port. Node port allows us to access applications running inside Kubernetes cluster from the outside world. I already pointed out when a pod is deployed inside Kubernetes cluster, we can't access it directly from the outside because pod gets private IP address which is accessible within the cluster. To expose applications to the outside world, one way is service type node port. For example, let's take 3 nodes running inside Kubernetes cluster. I'm creating a service of type node port. Let's say 32,000 is the node port of this service. This service is load balancing two pods. Here, node port means what happens, Kubernetes opens this port on all the nodes inside the cluster. In our case, we have 3 nodes. It opened 32,000 on each node. From the outside world, if we send requests to any node, take IP address of any node, put port number 32,000, the traffic gets routed to the service. That in turn forwards traffic to the pods. This is how node port concept works. Let's create a service of type node port. Keep in mind, there is a specific range for node port. It must be in the same range. The range should be between 30,000 and 32,767. Let's go to service. This must be node port. Along with target port, we can mention node port. If node port is not mentioned, Kubernetes will pick a random node port in a given range. If applications running outside the cluster want to connect with this service, they should use node IP, any node IP with node port. And if applications running inside Kubernetes cluster want to connect with this service, they can go with 80. This port is internal port. Node port is external port. Target port is nothing but when we send request to service, it forwards that traffic to the pod which is added as an endpoint on 8000. Let's see the pods running inside the cluster. kubectl get pods. Let's also get service details. I changed cluster IP to node port in the YAML document. Let's apply those changes. kubectl apply -f pyapp pyapp service. It is configured. Run kubectl get service and see here, previously it was cluster IP, now it became node port. Because we mentioned node port in YAML document, it is picking the same node port. If I don't mention the node port, what happens? It picks a random port number from a valid port range. If your Kubernetes cluster is running on cloud or it is set up on a bunch of machines with kubeadmin, what we can do is to test this, pick up one node public IP, send request to that IP on node port, it works. But in my case, it is not like that. It is a mini cube, right? I have a laptop. Inside that Docker desktop, inside Docker desktop, minikube is running. So to test this, we have a different minikube command. Minikube service name. And see that. It opened a tunnel between my laptop and with minikube server, I'm able to access it. Service type load balancer. This type of service also allows the applications running in Kubernetes cluster to be accessed from the outside world. The major difference between load balancer type and node port is, in node port, clients access the service directly on the port which is open on every node inside the cluster. But in case of load balancer, what happens? Kubernetes will provision a cloud native load balancer which will take care of load balancing all the nodes inside the cluster. Here, the cluster should be set up on a supported cloud environment only then Kubernetes can create the underlying cloud native load balancer. For example, if we have this cluster on Amazon Web Services, right, it uses Amazon's load balancer. If it is on GCP, it uses GCP load balancer, Azure load balancer. If you see the traffic flow, when a client sends request to this load balancer, it forwards the traffic to one of the node. That in turn forwards to the service. From there, it forwards to the pod. That's where our application is running. Last service type in our discussion, external name. This is a special type of service in Kubernetes. This will not create any real service. It doesn't do any load balancing. Rather, it acts like a DNS lookup. For example, we have API running outside Kubernetes cluster. Its DNS name is api.javahome.in. When I create service type external name, I provide a DNS record information. Let's say in this case, I'm giving api.javahome.in. So what happens when any pod sends request to external name? What happens? It provides the DNS name of the external application. Then pod directly communicates with API endpoint. Let's see how to assign pods to nodes. In Kubernetes cluster, there will be one component called scheduler. We will discuss more about this in Kubernetes architecture. Suppose using kubectl command, I want to deploy a pod onto Kubernetes cluster. I send that information to the cluster where scheduler come into picture to find the right node to schedule this pod, right? Suppose scheduler decided to put this pod on blue node. That is the job of the scheduler. Scheduler is really nice, good, brilliant. It does its job. But in some cases, we want to have little more control on where to schedule our pods. And let's take one more example here. There are 3 nodes with 3 different system types. First one is SSD, then CPU and memory. Think like this. We may deploy microservices onto this cluster where certain microservices are CPU intensive, certain memory intensive, and few they perform well on nodes which is SSD optimized. In such cases, scheduler may not know we are deploying CPU intensive workloads or memory intensive workloads. In such cases, we want to take control of scheduling. Now, for instance, we want to deploy a pod onto Kubernetes cluster. This pod requires better CPU. Now, I want to tell my scheduler, boss, please deploy this on any node which provides optimized CPU. In our example, I am showing only one node with CPU, but in real world, there could be multiple nodes with CPU optimization. So here we want to explicitly tell scheduler, please deploy it on the node which is CPU optimized. Accordingly, scheduler will deploy it on the node which is CPU optimized. This is what we are going to see in practical demonstration. To understand this further, we're gonna label nodes. While deploying a pod, in the pod specification, we're going to add extra information to tell scheduler this must go onto a specific node with specific label. Labels play a key role in this case. Let's jump into demonstration. I want to start this demonstration from clean state. There are no pods running on the cluster. Let's also check how many nodes are running for Minikube. kubectl get nodes. There are 3 nodes. Perfect. The first approach is very simple one. Let me get that information from Kubernetes documentation. Let's see node name. This option inside pod specification, I can directly specify name of the node on which this pod has to be scheduled. Like this. This is coming parallel to containers in sense under spec. After pod specification, let's give node name. Suppose I want to deploy this on Minikube node. This is name of the node. It should be scheduled on this one. If I want to schedule it on the second one, then I should provide name of the second one. kubectl apply -f PyApp deployment. kubectl get pods -o void because I want to get node details where this pod is scheduled. It created 3 replicas. All 3 replicas are scheduled on Minikube because we are explicitly telling it should be scheduled on Minikube. Node name option is very simple and it is direct because we are telling go and deploy it on a specific node. If node name is not found, pod gets into pending state. Let's give a wrong name, Minikube 123. Remember, there is no node with Minikube 123. Let's do kubectl apply. It is getting reconfigured. Run kubectl get pods. See, by the way, what is happening, because deployment has rolling updates concept, before deleting any of the running pods, it's trying to create a new pod. And see, it is trying to get onto Minikube 123, but this node is not available. Obviously, Kubernetes cannot schedule on Minikube 123. Probably it is going to struck here. Let me do one thing. Let me delete everything, again deploy freshly. So ultimately, yeah, everything should go off. Fine. Now do kubectl apply -f deployment file name and go and get the pods. Of course, right? There is no node with name Minikube 123. So that's why everything is under pending state. The point is, when we use node name, if there is no node with a specified name, pods will get into pending state. Let's change the name and fix the problem. kubectl apply yeah, 3 pods are in running state. Let's use -o void to understand where exactly those 3 pods are scheduled. Eventually, 3 pods which were in pending state gets terminated. This is node name. Let's move on to next approach for scheduling pods onto the nodes. So from the document, let me go to the top. Node selector. Click on this. How node selector works? We provide labels. See, in case of node selector, there could be multiple nodes matching the label. But if I give node name, there is no chance for multiple nodes. It has to sit on single node. So under node selector, yeah, provide node selector. Under that label, it has to check for on the nodes and put it on those nodes. Let's copy this, remove node name and bring node selector. Let me change this to systype SSD or CPU. Let's deploy this. I want to delete the old deployment. Because I want to freshly deploy this one. kubectl apply, get pods. See, these pods are also stuck in pending state. I will tell you why. Reason is simple. It is looking for nodes with label systype CPU, but there are 3 nodes, of course. No node has this label. Remember, when you do such node selector configurations in pod specification, make sure node also has these labels. So kubectl label nodes, name of the node, systype equals CPU. Out of 3 nodes, 1 node has this label. And see this one. When I run kubectl get pods, all pods are in running state. Previously, they were in a pending state because there was no matching node with a specified label. Now it found a node with specified label. It is running on that node. We are done with 2 approaches. Let's see the last and final approach. Let's go back to the list of approaches. Go to the top of the page. It is affinity and anti-affinity. I am going to show only one concept under this, that is node affinity. This approach, it is almost similar to node selector. It works based on labels, but it has little more flexibility. In case of node selector, when I give a label, it will go and find nodes with that label. If it is found, it gets deployed. If it is not found, it will get into pending state. But in node affinity, the flexibility we have is we can say mandatory or optional. So when you say required, see these 2 options we can configure. Required during scheduling. Required means mandatory. If nodes not found with specified label, pods cannot be scheduled. That should be in pending state. The second option, preferred during scheduling. In this case, preferred means optional. If there are nodes with matching label, deploy it. Otherwise, still okay, put it on any random node. The second part, ignore during execution. After a pod is scheduled onto the node, if someone changes the label, ignore it. Don't again bring it back to pending state. That is the meaning of ignore during execution. Let's copy this. Let's use it here. Key systype We can specify multiple values for a given key. So now, according to node affinity configuration required, at the time of scheduling, it is mandatory. If no node found with a specified labels, do not schedule. And ignore during execution means once it is scheduled, if someone is changing labels on the node, please don't care, leave it, let the pod keep running on that machine. Let's deploy this. I want to delete existing deployment and create it freshly. So kubectl apply -f deployment file. And see that everything getting onto minikube because minikube node has the label systype CPU. That's all about scheduling. Let me walk you through auto scaling pods. We got horizontal pod autoscaler, which is responsible for automatically scaling pods that are running behind service. Before I get into horizontal pod autoscaler, I want to make you understand what is scaling. Let's take application with two replicas. When traffic increases, automatically the resources like CPU and memory has to increase to absorb the extra load. This is nothing but scaling the application. This can be done in couple of ways. We can maintain same number of pods, let's say only two, increase CPU and memory of the pods. Second option, instead of increasing CPU and memory of existing pods, in this case 2 pods, we can add more pods. That is also fine. So in this case, one is called vertical scaling, where number of pods remain same. We increase CPU and memory for those pods. Coming to horizontal scaling, we add more pods to capture the additional traffic coming to this application. Let's see how horizontal pod autoscaler functions. It reads pod metrics from the metric server. If metric says we need to increase number of pods, it sends scale instruction to the deployment. Let's say it want to add one additional pod. Deployment in turn manages replica set. Replica set creates that additional pod. This is how horizontal pod autoscaler functions. Let's see the demo of horizontal pod autoscaler. First, I want to show you how to scale manually. Afterwards, I will show how to automatically scale using horizontal pod autoscaler. Right now, we don't have any pods running inside Minikube cluster. Let me show the content of PyApp deployment. Let me open this in Visual Studio Code. Deployment. I don't want affinity here. Let's deploy the deployment file. According to deployment specification, it has to create 3 replicas. PyApp is the deployment name. It is running 3 replicas. Those 3 replicas are in running state. If I want to manually scale, the command is kubectl scale deployment slash deployment name hyphen scale equals 6. Currently we have 3 replicas. I am scaling that to 6 replicas. It is not scale. Replicas equals 6. kubectl get pods. We got 6 replicas. 3 of them are showing 4 seconds, which are just created after running kubectl scale command. This is manually scaling pods. But in real world, when we have larger environments, many microservices, we can't really sit, monitor the metrics and go and run scale command. It is not possible. Instead, what we want to do is we want something which monitors the metrics and takes a decision of scaling, like scaling out, nothing but increasing number of replicas, scaling down, reducing number of replicas when traffic reduces. Let me run scale command again. If I want to scale it down, let's say 2, now it gets scaled down. It has just 2 replicas now. For horizontal pod autoscaler to work, there are 2 important points. Number 1, we must enable metric server. Otherwise, horizontal pod autoscaler cannot read pod metrics. If it cannot read pod metrics, it cannot perform automatic scaling. That is number 1. Number 2, in the deployment file under pod specification, we need to explicitly mention the resources, CPU and memory. These 2 are important for horizontal pod autoscaling to work. So let me add resources section to this. So it's suggesting this piece of code. I want to keep it. Resources, requests. This is the minimum memory CPU required for this pod. Limits, right? It is maximum. I'm good with random values here. Run minikube add-ons enable metric server. This command will enable metric server inside minikube. To see list of add-ons inside minikube cluster, run minikube add-ons list. Notice this metric server is enabled. I want to create horizontal pod autoscaler specification. Create HPA for the deployment. See, because I'm using agent option, it will not just tell me how to do it, it will do it. It's going to create that file for us. I say keep. It created PyApp HPA. Let's see what this configuration file does. It is telling which deployment object to scale, right? PyApp is the deployment name. Minimum replicas to maximum 5, meaning the scaling happens between 2 and 5. Under metrics, it is going to monitor CPU of the pods. It's going to take average CPU utilization of the pods running under this deployment. If it exceeds 50%, it will add new pods. When it goes below 50%, it will do scaling, that is nothing but remove pods. It has to keep number of replicas between 2 and 5. I want to deploy everything from scratch. Let me delete service and deployment. Likewise, delete service. I think it is PyApp service. Let me create everything from scratch. Let's create deployment, then service, followed by horizontal pod autoscaler. Usually it takes little while to show up the metrics here. Let's check again. Yeah, now it is showing up. Because we don't have any traffic, current CPU average utilization is 0%. Let's use a tool to increase the load and we can test how autoscaling works. Let's use WRK tool, which is a performance testing tool. The command is WRK. Here T means number of threads and other details. I need to provide the URL of service so that when load goes to that service, CPU utilization in pods increase, then autoscaling comes into picture. So let's run this command in a separate window. But on MacBook, we can't directly hit Minikube IP address. I need to open a tunnel. So there is a way to do that. Minikube service name. So it opens a tunnel between local laptop and service running inside Minikube. Let's enter. This opens a tunnel between local host and service running inside Kubernetes cluster. This is the URL we want to hit using performance testing tool. So here, provide the URL. In the end, you must mention CPU. Let's open one more tab and monitor HPA. See there, the CPU utilization is gradually increasing. It was 0, now it has become 1. Looks like the tunnel is closed. Alright, let's run performance testing command again. Instead of sending this request for 30 seconds, let me make it 500 seconds. Okay, I think the port number got changed. So copy this. So here, let's update the URL. Yeah, see here, the CPU got increased. It went up to 59%. Previously, number of replicas was 2. Because of increase in average CPU utilization, number of replicas has become 3. This is how horizontal pod autoscaling works. Now let's discuss about Kubernetes Ingress. This is very important concept. First of all, let's understand how things work without Ingress. Suppose we have an application running behind a service. To expose this application to the outside world, we can either make it node port or load balancer. Let's go with a load balancer. What happens in this case, if you deployed this on Amazon Web Services, it creates a load balancer inside Amazon. Using that, outside world can access this service. Okay, but generally when we use containers, Kubernetes cluster, usually we deal with microservices architecture, meaning the big application is divided into smaller services, like where each and every service will have a single purpose. So we're going to have multiple services inside the cluster. If there are 3 services, if we want to expose all 3 using load balancer, we need 3 load balancers. If we are dealing with 50 microservices, we end up having 50 load balancers. But this is not a viable solution. Rather, what we want to do is bring Ingress into the picture. What Ingress does, it will give a single endpoint for the outside people or applications to talk with services inside Kubernetes cluster. Remember, 3 services, we don't have its own load balancers. We are declaring them as cluster IP itself, meaning they are private. If user want to access service 1, so what happens, he hits the endpoint of Ingress. Okay, this is going to have routing rules. Rules will be like the host, from which host the request is coming. I'll show that after this presentation. And rule 1, let's say, if path is /svc1, it will route traffic to service 1. If path is svc2, it routes to service 2, and likewise. While dealing with Ingress, we come across 2 components. First one is Ingress itself. So this defines rules which tells how external traffic should reach services inside the cluster. Remember, Ingress handles only HTTP and HTTPS. We can also configure TLS certificates at Ingress level, where the communications coming into the cluster can be secure. The second component is Ingress Controller, the actual implementation that makes those rules work. Whatever rules we define in Ingress, that implementation is part of Ingress Controller. Kubernetes directly doesn't provide Ingress Controller for us. We have a wide range of options available in the market. We should choose one which best suits our requirements. Let's get into the demo. We are taking 2 applications, Apple, Banana. Treat Apple as a microservice and Banana also a microservice. In apple.yaml, I declared deployment details along with the service. I'm taking HTTP echo image. This is an image available in the internet. So whatever text you pass, that text is shown on the browser. So for Apple deployment, I'm saying this is from Apple service. When request goes to Apple service, this is what we see. All right. And this is deployment. This is the service which handles traffic for the Apple deployments. Likewise, we got Banana, a separate deployment for Banana. We are using same image, but the output coming from this application is different. So we have 2 microservices, Apple and Banana. Then comes the Ingress. Okay, I'm using Nginx Ingress Controller. What we see on the screen is if traffic is coming from javahome.local, it should come from this host. It has 2 paths. I told you, right? Ingress contains rules. One rule is if traffic is coming from javahome.local, it got 2 paths. One is Apple. If request is coming from javahome.local /Apple, This routes traffic to Apple service. In case if it is coming with javahome.local/banana, this is going to route traffic to banana service. This one. Alright. So let's deploy this, but before deploying, I told you while dealing with Ingress, we have two things. One is Ingress, the rules. This is nothing but Ingress and it is containing rules. To implement these rules, we need Ingress Controller. Because we are testing this in Minikube, we must use a specific Ingress Controller. We should say Minikube. Okay, I have readme.md file. You can follow these instructions. Enable Ingress. Okay, we can check if Ingress is enabled. Minikube, add-on, list. You can see this one. Ingress is enabled. The second step is configuring the host file. Let me come to this later. Then apply apple, banana and fruits Ingress. Let's do that. Enter. Let's deploy banana. Let's also create Ingress. The next step is Minikube tunnel. Okay, in my laptop, what is happening? We are using Docker desktop on top of MacBook. Inside that Minikube, we are deploying Kubernetes components. The problem is we can't directly access Kubernetes from my local laptop. To fix this problem, Minikube has provided a solution, that is open a tunnel. When you run this command, it opens tunnel between my local laptop with Kubernetes cluster so that I can use my browser or terminal. I can directly talk with Kubernetes. This command opens tunnel on my local host, that is 127.0.0.1. So that's the reason I need to update a hosts file. This is nothing but local DNS. I mean, if you put google.com in the browser, what happens? In the background, the DNS comes into picture. That DNS is internet DNS. So it goes to the internet DNS. From there, it picks the actual endpoint and browser uses that actual endpoint to access the Google application. But in our case, what happens when we put javahome.local, it checks my local DNS, nothing but this file. So based on this host, it should route traffic to this local host. That is where my tunnel is created. The tunnel is created with localhost to Kubernetes cluster. So we should open this file, edit, add this entry in that file. I have already updated this. Let me show this file for you. Cat etc hosts. See this entry. This entry is must. Let's open the tunnel. Remember, it opens tunnel between my local host and Kubernetes cluster, which is on Minikube. I need to enter the password. Now the tunnel is open. Let's open the browser and test it. Before I put things in browser, remember the host name should be this /apple. The request goes to Apple service and we should see a response from Apple service. Let's test this. I'm in the browser, Apple. Now, the moment I put this, browser checks my local DNS, that is hosts file. There, we mapped jahome.local with localhost, that is 127.0.0.1. Apple. We should see a response from Apple microservice. Yes, it is. If I change the path and make it banana, I see the response from banana service. Now we got single endpoint, that is Ingress and Ingress Controller, taking care of routing traffic to multiple microservices inside the cluster. Let's have a look at Ingress file. Say this. Host is this /Apple. It is forwarding to this service. When host is jahome.local /banana, the traffic is going to banana service. This is how Ingress Controller works.